Yeah, my talk today will be centered around building a trustworthy AI. There's a lot of topics out there talk about this subject. What I would like to do is to give our view from regulated industry in financial institutions such as banks. So we'll focus particularly on the issue of explainability and robustness. This is the two main topics that we care about and very important in the regulated industry. As you know, a bank runs by model. We use a lot of model in banks to do both financial and non-financial models. Financial model are the traditional model that bank always do for many years. This in the area of credit, market, liquidity, revenue, expense, loss, stress testing, capital management, etc. And then in the non-financial side, this is dealing with customer service, financial crime, marketing, compliance, conduct, staffing, etc., etc. Now, for us, when we use model, we believe that all models are wrong, and when they are wrong, they create risks, both financial and non-financial risks to the institution. With that, model risk management is very core and center in the industry to manage model in the end-to-end life cycle. In this particular talk, I'm going to talk in particular in terms of machine learning and the rapid adoption of machine learning in banking. So we use a lot of machine learning to do both as a statistical model, as an alternative to statistical model, or we also use it as a model benchmark. The model that's in production probably is still statistical model, but we use machine learning to as a benchmark, or we use machine learning to do that model diagnostic or variable selection and construction of the model, even if the final model is the traditional statistical model. So that's in the area of that traditionally have a lot of statistical techniques like credit risk and financial crime, fraud, etc. And then another area that previously no model. So this is area in compliance, conduct risk, customer assistance, a lot of the natural language processing model in this. The other area that we use a lot is also area that's traditionally computationally is very intensive, such as derivative pricing when we're dealing with high-dimensional stochastic differential equation for equity basket, for example. That's very difficult because we're dealing with high-dimensional PDE and simplification has to be made. So we also use deep learning as a way to solve high-dimensional stochastic differential equation. So before I go to delve into some of the example and what we care about in terms of explainability and robustness, let's talk about model risk, because this is a very important in the in financial institution. As I said, we believe all models are wrong, and that's the famous quote from George Sparks. But what we care a lot is when models are wrong, they potentially will harm or create unintended consequence to the user, to the institution, or the customer. So when models are wrong, they create harm, can be financial harm in credit, market, liquidity, with loss, credit loss, or loss in the on the market side, or potentially also creating non-financial harm, which in terms of reputation, compliance, and legal. I give a few examples here, both financial and non-financial. In financial, if the model is used for hedging, the model wrong happen with mishedging that generate market risk. In financial crime or conduct surveillance, when the model wrong, the model will misdetect and they generate compliance risk. In staffing, is understaffed, long wait time, and create reputational risk. Credit approval, we use a lot of credit model to approve credit. Sometimes, yes, we do have type 1, type 2 error, but also we have unintended consequence, which dealing with fair lending. Model make discriminatory based on protected class. That's create a compliance risk. Another example that sounds very mundane in terms of online marketing. When you do you log in to your banking system online, you will get product offering. It seems very mundane. So what's the harm in there? People click and don't click. So it sounds very harmless, but in reality is those models created based on cookies, information in the cookies, what website that the person visit, etc., etc. Now suddenly we're dealing with privacy and fairness. People with different demographic, younger generation and older generation, they have different behavior online. What website do they visit? And if people get different product offering, that create fairness issue that generate legal risk. So this is all the things that we care a lot in the financial institution dealing with the model risk. And we know, as I said before, all models are wrong. And when they're wrong, they create damage. And when we're using model, we're taking model risk. And when we take model risk, we better off know what kind of risk we are taking. So one of the things, if I come back to the machine learning model risk, there are a lot of things that can go wrong, and the source of model risk, a lot of people talk about data defect and bias. That's the implicit bias coming from the data. Conceptual soundness, we'll talk about this in deeper. This is related to explainability, how sound the model is. So that's very important, and particularly in the machine learning world, because we're dealing with large number of variable, it will have a lot of spurious variable effect. So we'll talk about that. Model robustness, this is very important. A lot of people in machine learning obsess with model performance. So they do hyperparameter tuning, do auto machine learning to optimize the model based on the data split between the testing and training data split. Real world is dynamic, data drift. So you can build model that's the best based on the data splitting, based on your testing data. When you put it in production, can be complete failure or miserable. Model change control are very important, because every time we retrain model, because we're dealing with highly non-parametric model. Basically, when you retrain, you change the model. So we better know what has changed and how to deal with that. A model use control. This is a model will make mistake. Model will do wrong. So what are the and model will use in different environments. So how would you control that? My talk today, I'm going to focus on the conceptual soundness and model robustness. They're dealing with explainability and model robustness. Let's talk about the explainability. One thing that we need to pay attention a lot is outcome testing is not sufficient. So a lot of people, when they build model, do machine learning, we have testing data, separate testing data, based on testing data, make decision whether this is sufficient model, good model or not good model. In the auto machine learning, they try all kind of different model and pick the one that's the winner based on the testing data. That can be very dangerous exercise. Why? Because we need to ask question, does the model make sense? Can we trust the model? How's the model going to fail? And for critical application, for mission critical application in a high stake environment, explainability is a requirement. So a lot of machine learning application today, it's somewhat not in the area that is high stake environment, but in the high stake environment is very, very important. For example, for us, when we use for, let's say for decisioning, for example, let's say credit decisioning, it need to have a recent code when credit is declined. This is a regulatory requirement. So explainability can be very, very critical. But also more importantly is what we call as a conceptual soundness. Is the model make sense? Can we trust the model? How is the model going to extrapolate? So this is the type of fundamental question that we need to talk, and we're going to delve more deeper on this. I talk about the issue of robustness, real world and dynamics, how model going to perform in production. In adversarial environment, model can perform, can operate in adversarial environment. For example, for us, when one of the applications that we do is to monitor trader behavior. So a lot of things you read in the news in terms of some banks get penalized because of the trader misconduct. So people put machine learning to monitor the chat or the email traffic from traders, and in that situation, model operate in adversarial environment. The people that being monitored, they will try to find a way to circumvent the model. So testing for robustness, how the model can be circumvented, are very, very critical. I would talk about a little bit because of the obsession of people in machine learning in terms of performance. AutoML, like I said in previous things that I mentioned about, people do a static split between training and testing. So data splitting is misleading. So we need to test it, how to look at the robustness of the model. What situation that the model decision will flip. So that's what we talk about model robustness, and we'll talk about this a little bit. I'm going to mention a little bit in terms of explainability that relate to the interpretability. Explainability is more in the sense that can you explain it to the user, and from that you need to do that you need an interpretable model. And a lot of techniques today in the interpretable machine learning, from post hoc interpretability, treating model as a black box, and then applying tool like LAMP, SHAP, PDP, and a whole slew of post hoc analysis tool try to explain a black box model, how the model behave. Other techniques is called model distillation. Basically, coming up with a simplified model, so that with the simplified model, we can explain. For example, we do a gradient boosting machine model, and then we put distillation model simple tree, and at the bottom, at the node of the tree, you have a linear model, and you can interpret the linear model at the bottom of the nodes to the simplified model. The focus that I want to talk a little bit more is really the self-explanatory model. Can we build machine learning, sophisticated machine learning that is self-explanatory, just like the traditional statistical regression, the good old French statistical model like regression in statistics? So that's what I call as a self-explanatory model. How can we build machine learning model that is self-explanatory? So one of the things that we do a lot, and there are a few techniques, and I'm going to talk about this very, very briefly, and then we're going to talk about deep neural networks, how to make deep neural network as a self-explanatory model, because the answer is yes, we can. In what we call it, the first thing that we can do is really to constrain. This is several alternative way to do it. I'm going to go to the first one, is by constraining the deep learning to make it self-explanatory. One of the way to do it is we creating from input, we creating what we call it is a projection layer. very, very few projection. In this example, let's say 1, 2, 3. You project it into 3, and once we project it, we have a univariate, a single projection. And then we put the deep network to do the nonlinearity, and then we combine it at the end. So we have projection layer, we have the deep layer to do the nonlinearity, and then we have combination layer. So the key here is really to make the network more sparse, not too many sub network, very few sub network. So that will make it more clear, and we know what the sub network do, and then very, very sparse in the input as well, so the projection can be interpreted. If you look at the projection layer, it's just simple regression. It's a regression because a linear regression, and then we have nonlinearity. So I'll go to that very, very quickly in the sum of example. Here is an example in the projection. We can see what variables are important and what nonlinearity that is built by each sub of network. So make the model interpretable. The second thing is another techniques that people do is called adaptive explainable neural network. So here is we're doing it a multiple step. The first step is build model based on the individual variable with nonlinearity, and then combine it in statistics that call generalized additive model. So that's very, very interpretable model. And then after you got the generalized additive model, you can build model with interaction to model higher interaction, and then you combine it through either boosting or stacking. So you can get the effect of individual variable as well as interaction very, very clearly, as in the case of statistical model. Let me talk about this subject. How about fully connected deep ReLU network? Fully connected deep ReLU network is local linear model. We can interpret it very, very easily. For example, in this example, for after you train the network, you can trace it for each sample. You can trace it what activation, what node are being activated. And if it's ReLU, which is basically is piecewise linear, so we can get all the linear model coming from the node, how it's a combined combination of linear model, still linear model. So you got the linear model. So in this example, you can trace what are the linear model are being used for a certain sample. With that, you can go through each sample data. You can get all the equation, all the linear model that is coming from a deep ReLU network. And if we do that in this example, we can plot the coefficient, which is what are like regression. Just like linear regression, you can plot all the coefficient using very simple parallel coordinate. In this is the horizontal are the variable, and the vertical are really the magnitude of the weight or the magnitude of the coefficient of the regression. You can see what variable are important and what variable are less important. And we can also see how the deep learning, the deep network partition the data. For example, we can use this one as diagnostic. You can see this is the biggest, the region 0 is the biggest sample. It has about 80% of the sample, and the performance is not as good. Or you can look at things, and actually, if you look at the deep network, many region or many equation only have a single class. This is a classification problem. So a lot of inefficiency in the deep learning that you can simplify model further to have less number of equations. Bottom line is deep learning using ReLU network is local linear model. You can get all the local region, you can get all the equations. Some of you that interested in this more deeper, we will have paper that we're going to publish in archive within a week. So stay tuned. You can learn that in more detail. We can apply this to word embedding in the natural language processing, word embedding, convolutional neural network. We can apply all of those to come up with explainable neural network. Because I have limited time, let me do one last thing that I want to talk about, the issue of model robustness. As I mentioned before, model can operate in the when you put model in production, the environment will change, data will drift, or it operate under adversarial environment. We need to make sure we understand how robust the model is, how the model can be tricked. So in this example, because of the local linear model of deep learning, we know all the local linear equation, and we need to perturb how much perturbation in the data that will make the decision flip. So in this example, if it's local linear model like a deep ReLU, we can get exactly the distance to the local decision boundary, and we can perturb and we can see how robust the model is. So this example, apology, I think my alarm there. In this example, for example, the example that I showed before, and we look at the region, how to make this model, how robust this model is. So you can compare two different model. In fact, we look at the original deep learning coming out, the decision boundary from deep learning, compare if we retrain locally, how can we make it more robust? So you can see with a perturbation, a slight perturbation, how much more error the model will generate. So this one here, the original deep learning, it's not very robust. With slight perturbation, the error increasing, when the other alternative with the perturbation, the model still performing very, very well. Let me bring back a little bit about the issue of robustness that I talked about before. When model operate under adversarial environment like traders monitoring, people can change the character, people can change the word, people can change the sentence. Other side of conversation, human beings still understand that, but machine can be fooled very, very easily. So testing for model robustness, performing perturbation, so that we understand how the model can be wrong is very, very critical, and how much wrong the model will be very important. In particular, like I said before, all models are wrong. We need to understand how wrong can it be? How can it be wrong? It's core and center when we apply machine learning, and with that we require somewhat more sophistication compared to more traditional model. I will stop right here because I think I will have about 3 minutes to do Q&A. So we'll be happy. Let me stop my sharing, and we'll be happy to answer some of the question here.